So we're in section 13.2, and we're talking about multivariable functions, and we want to talk about the limits and continuity. So the ideas are pretty much the same as the ideas with limits and continuity that we've talked about with single variable functions, except we just have another variable. So that introduces a couple of interesting little twists when we talk about limits and continuity. And the idea of a limit, the idea of continuity is we're talking about when we have values, when things are close together. We want to figure out when things are close together. How do we quantify that? If they're close, if we have two domain values that are close together, we hope in our function then that gives us two function values that are close together. And the idea of a limit tells us what close together means. So do we remember in single variable calculus, in calculus 1, how we define a limit? It was probably your favorite thing to do. Epsilon-delta, yes. Beautiful epsilon-delta. Epsilon-delta is the definition of a limit. That's really, it's the crux of calculus, is what is a limit. That's what calculus hinges on, is this idea of a limit. And epsilon-delta, the epsilon-delta definition gives us a formal analytic way to define what we mean by close together, essentially. So I'm going to write our definition of our limit for a multivariable function, a two-variable function, talk about what it means, and we'll go from there. So f of xy is a function of two variables. And the definition is the same if we have more than two variables. It's just we just add the variables. And L is a real number. The limit as xy approaches x0, y0 of f of xy equals L if for some epsilon greater than 0, and I like to add no matter how small, because we're usually talking about a small epsilon. We want our distance to be close. So some epsilon greater than 0, no matter how small, there exists a delta greater than 0 such that if 0 less than the square root of x minus x0 squared plus y minus y0 squared is less than delta, implies that the absolute value of f of xy minus L is less than epsilon. So this definition tells us what we mean by close together, because limit is really telling us something about when things are close together. So our definition tells us that when our domain value x0, y0 is close, they're close together because we're trying to make it this small number. That implies that our function values are close to the limit. So if we get close to a specific value in our domain, we should get close to our limit in our range. And this epsilon greater than 0, no matter how small, says no matter how close we want our function value to be to our limit, we can find some domain value that's close to some specific value that guarantees us that we're that close. We call this quantity the square root of, and if you go further in math, this will play a big role. This quantity x minus x0 squared plus y minus y0 squared is called the delta neighborhood. The delta neighborhood about x0, y0. Or you can, it's also called the open disk. Open disk is the way that I normally heard it. And we'll draw a picture here in just a second to kind of look at what this means geometrically. So this is an open disk about x0, y0 with radius delta. And the idea of an open disk or a delta neighborhood, if you go further, if you study analysis at all, analysis is what is making all the theorems that we talked about in calculus, making them rigorous. You talk about open disk, this idea of an open disk or a delta neighborhood really plays a central part in that. So let's draw a picture and see what this means graphically. So we know what our definition of a limit is. It's the same as the one we use in single variable calculus. Let's look at a picture. So if we draw a picture of our open disk. So if we're in the xy plane, because our open disk is our domain. So here's our xy plane. So we have some region in our domain. So let me get a circle. Why is this not dotted? Okay. So in the xy plane, this is my open disk. The center here is x0, y0. The radius is delta. And everything in the interior of this open disk is where the square root of x0 minus x minus x0 squared plus y minus y0 squared is less than delta. So everywhere in the interior of this circle, this dotted circle, so we're not talking about the boundary, that's why we call it the open disk. Everywhere in the interior is where this is true. So if we're looking for, in our definition of the limit, we're looking for a delta inside this circle. So we want the delta to be inside the circle, so we're trying to get something that's close to x0, y0. And if we draw this, what the limit means in 3 dimensions. So here's our three-dimensional coordinate system. And what I'm trying to do here, I want you to have kind of an intuitive idea of what we're talking about with this definition of a limit. We're not going to do any epsilon-delta proofs, but I want you to have an idea of what this means. So if we're in the xy plane, and here's our open disk in the xy plane. And this is x0, y0. And we have some point in our open disk, xy. So if we're inside this open disk, what our definition of limit means is we have some function up here, and our function is a surface. So here's our surface up here above the YZ plane. And I'm going to project this open disk up onto the surface. So we get some kind of shape up here. Now if I project this over onto the z-axis, the maximum value of the function here and the minimum value here. Here's my limit. This point is L plus epsilon, and this point down here is L minus epsilon. So when we're inside this open disk in the domain, our definition, if we have a limit, if our limit is L, that's going to guarantee that I'm in this little band of values for my domain value. So if I'm close in the domain, I'm close in the range. And our definition tells us that no matter how small we pick epsilon, we can find a delta such that this condition is guaranteed, that we're close up here when we're close down here. That's what our definition means. Now there's an important distinction between function of two variables and single variables when we're talking about limits. When we're talking about a single variable function and we're working with limits, what do we have to be careful of? When would a limit not exist with a single variable function? When there's a cusp. And so what happens to your function value? So it's not continuous. So how did you figure that out with a single variable function? Not differentiable. Let's go even more basic. If it's undefined, so when you first talked about limits, didn't you talk about approaching from the right and from the left?
Yeah.
And if they didn't approach the same value. Well, with a multivariable function, with a two-variable function, it doesn't really make sense to talk about a right and a left, right? Because we could approach from any direction. So for a multivariable function, our limit has to exist no matter what path we approach our value from. If we approach our value from two different paths and we get two different limits, it could be any two paths. There could be one single path that we could approach where our limit doesn't exist. That would mean that that we have a problem. So for a multivariable function, we can approach our value here from any path. So that's an important distinction to remember about limits for multivariable functions. We can approach on any path. Any questions before we go on? All right. All the rules that we talked about for limits for single variable functions hold for multivariable functions. So all of our limit rules are the same. And those include sums, products, quotients. multiplication by a constant, they're all the same for multivariable functions as they are for single variable functions. One important thing to remember, especially that a result that comes from single variable functions that we need to remember is that limits of polynomials and rational functions and we like polynomials because they behave nicely, and we like rational functions because they're ratios, they're fractions made with polynomials. We find the limit by evaluating the function at the point that we're interested in. So if we have f of x, y, the limit as xy approaches x0, y0 is just the value of the function at x0, y0. As long as a function is defined there. So polynomials and rational functions behave nicely when we're looking for limits. So that's going to be an important one to remember. So before we go on, I want to work on a couple of problems. So in your book, on page 902, number 5 through 8. Look at those 4 problems and come up with those limits. This should go really fast. Number 5 through 8, page 902, number 5 through 8. So it's just we're just looking at combining, working with the properties of limits on those. All right, pretty easy, right? What do we get for the first one? 2. We're just subtracting. What about the second one? 20/3, just dividing. G of x doesn't equal 0, so we're okay there. How about the third one? 15, we're just multiplying. And the last one? 2/5, right. So we're just combining our limits just like we've done with single variable functions. Now keep your books out because we're going to be looking at some more problems in just a minute. So this result is going to be important, that limits of polynomials and rational functions are just found by evaluating the function at the point we're interested in, and the limit exists everywhere the function exists. So let's talk about continuity, because continuity has something to do with limits. We want to talk about the continuity of multivariable functions. Our definition. It's very straightforward. F of x, y is continuous at x0, y0. If the limit as xy approaches x0, y0 of f of xy equals f of x0, y0. So our limit has to exist, and our limit has to be the value of the function at the point that we're interested in, just like with single variable functions. Our ideas from continuity for single variable functions carry over to multivariable functions, just like they did for limits. So we just like we talked about with limits, our limits, when we're looking at continuity, our rules, we can talk about scalar multiples. So if we multiply our function by a scalar, it doesn't affect the continuity. Sums and differences of continuous functions are continuous. Products and quotients. So all of these combinations of continuous functions are going to be continuous. And again, this implies that polynomials and rational functions are continuous. Everywhere they exist. So whenever we have a polynomial or rational function, we're dealing with a continuous function as long as our functions exist. Now, the last thing we need to deal with before we move on to our next topic, we'll start talking about derivatives tomorrow, is we need to talk about composite functions. Composite functions, we need to figure out how those work. Yes, it does. So we need to figure out how composite functions work. They're a little, there's a little twist when we're talking about multivariable functions. So for composite functions, if z is f of xy, if this is continuous, and g of z is a continuous function of z, then our composite g of f of z is continuous. Sorry, not z, g of f of xy. Or we can write that g of f of xy is continuous. And this implies that our limit, the limit is just the value of the function at the point that we're interested in. Now the twist here is that f is a function of two variables, and z is a function of one variable. So our composite function is a composite of a two-variable function and a one-variable function. And what this implies is that composites of continuous functions are continuous. So if we have a continuous function and we make a composite with a polynomial or rational function, that function is going to be continuous anywhere that our function exists. So when we can do composites of continuous functions and get continuous functions. And composites are really what we're interested in, really what we usually work with, because working with just polynomials or rational functions is very limiting. So we're usually looking at some kind of composite function, and we want to look at composites. If we know we're looking at composites of continuous functions, we have a continuous function. Now, with that in mind, any questions before we go on? Okay. In your book, on page 903, number 25 through 28, and then number 30. So look at number 25 through 28. We're looking at, we want to figure out we're discussing the continuity as x and y approach 0 and 0. And we want to figure out the limit as x, y approaches 0, 0 of those four functions. And then number 30, we're figuring out something about the limit of that function by evaluating the function. So take a look at those 5 problems. Again, this should be pretty easy. So number 30, we're looking at the limit of that function. We're trying to make a conjecture about the limit of that function approaching from 2 different paths. We got the first 4?
Yeah.
First 4. So the first one, e to the xy. Is it continuous? Yes. It's a composite of continuous functions, right? And how about the limit as xy approaches 0, 0?
1.
The limit is 1. We just evaluate the function at 0, 0. So our limit is 1. How about the second one, that rational function? The limit is 0. Rational functions are continuous everywhere they're defined, and there aren't any problems with that one. How about the third one? The limit doesn't exist. Is the function continuous? Everywhere, it's continuous everywhere except at 0, 0. So that one is not continuous at 0, 0, and the limit doesn't exist. How about the fourth one? Not continuous. Can't divide by 0. So our limit does not exist. And isn't that fourth one, isn't that kind of a cool looking function?
Yeah.
Do you use it like L'Hopital's around this at all?
So L'Hopital's, you can use L'Hopital's if you have something in the form 0 over 0 or infinity over infinity. And the cosine of 0 is 1.
So if you have 1 over infinity, that's 0.
That's right.
Right?
But if
Oh, I see. Okay, yeah.
so, you have 1 over 0 here.
And that's infinity, or is that just
That's undefined.
Okay.
If you had something like sine of x squared plus y squared over x squared plus y squared, then you could use L'Hopital's rule. You could say make a substitution, say w equals x squared plus y squared, so you'd have sine of w over w, and then you could use L'Hopital's rule to figure out that limit. How about number 30? What happens when to your function values when your path is along y equals 0? What's that? It gets really close to 0, 0. So our limit along that path looks like it would be 0, right? So what about on the path y equals x? What happens to your function values there? Plug those values into your function.
What do you want to be doing?
Uh,
The path x, y.
the path y equals x for that function. So you do like 1, 1, 0.5, 0.5. So as xy gets close to 0, 0, what happens to your function value? It gets really big. So what does that suggest about the limit of that function? Doesn't exist, because along two different paths, we get two different values for our limit. So plugging in values into a table of values doesn't prove that the limit doesn't exist. It suggests that it doesn't. So let me show you how you would approach something like that analytically. So we're looking for the limit as xy approaches 0, 0 of y over x squared plus y squared, and along y equals 0. So if we're going along y equals 0, we're just looking at the limit, and I'm just going to write limit, I'm not going to rewrite this, of 0 over x squared plus y squared, and clearly that's going to be 0. Now if we want the limit along y equals x, we're looking for the limit, and I'm going to substitute x for y here, because y equals x. So we get the limit of x over x squared plus x squared. So along y equals x, I'm just substituting x for y. So we get the limit of x over 2x squared, and that gives us 1 over 2x. So we're taking the limit of 1 over 2x as x is approaching 0, which is undefined. So if we were looking at that problem analytically, this was how you would go about showing that limit doesn't exist analytically. So our function is continuous everywhere except at 0, 0. And from the picture there, you see it does that weird thing at 0, 0 where it goes really high on one side and really low on the other side. Any questions on limits and continuity? All right, tomorrow we'll get into the good stuff where we start taking derivatives and we learn a nice new symbol, a new calculus symbol. So homework. Page 905. There you go.